Matthias is a student at UC Berkeley.
Postdoc.
And Boston.
Postdoc.
Ah, pardon.
No worries.
And he's really interested in security, virtualization, and exploitation. And his talk will be about using symbolic execution as a powerful way to analyze programs. Thank you very much.
Hi, thanks for the introduction. Welcome. No worries, no worries. Was perfectly fine. Good to be here, good to be back at the CCC. Last year, unfortunately, I didn't make it, although I made it here the 10th time now, so 10 times in 11 years, and I really missed it last year, and I'm so happy to be back. It's awesome. Even though the location is a bit different from Berlin, it's really nice to be back. For this talk, if the slides work at one point in time, I hope the debacle in the room one doesn't repeat itself. Can you guys? OK, awesome, awesome. Let me take you on a journey down to a rabbit hole that's symbolic execution. So, and let's follow Alice down that hole and see how far we can go. Symbolic execution has had a bad reputation for quite a while now. Many say it's overhyped, it's oversold, and people are promising too much. And in this talk, I want to discuss with you what it can do and also what it can't do. So what are the limitations of symbolic executions? How far can we go? What kind of things can we explore, and so on? What are the limitations, and how can we get around them? This is joint work with Stephen McCammond, who started all the amazing fuzzball stuff and who's the main contributor of the symbolic execution engine and maintainer of the engine as well. Dan and Alex, who did amazing reverse engineering work while they were at UC Berkeley, and a whole bunch of other students, interns, and so on that really helped us get along and get us that far. So almost all of the praise goes to them. I'm just delivering the message to you. So let's start with some of the preconditions when we're following down that hole. So there are actually a large set of tools that help you find bugs and discover bugs and so on. And we all know that finding bugs and crashes, that's the easy part, right? So getting something to crash, getting a seg fault, that's easy. There's fuzzing, there's bounded model checking, and test cases, and a whole bunch of other things that can help you to get to these bugs or to actually trigger the bugs. But the hard part then comes, how can we generate an exploit, or how can we find a specific form of input that travels along the path inside the application that will then trigger these vulnerability conditions maybe deep inside the program? How can we actually define all these little things that flow through the application that end up and come together at the vulnerability point where the bug is to actually trigger the vulnerability? Also, how can we cope with all the transformations that the input undergoes until it reaches the final point? And we'll look into how we can use symbolic execution to kind of trigger this point and follow down the chain deeper and deeper into the rabbit hole. So on a very high level, what we do, we assume that we have found some vulnerability condition inside the application. Maybe deep inside the application, hidden behind some form of transformations and so on. And what we do is, starting from that transformation, we walk back step by step by step by step until we hit the input of the program, some input that we can control, actually. And we will then generate a proof of concept input that follows down the chain of transformations until we hit the vulnerability. And for all that, we use, until now, an abstract form of symbolic execution, our magic box that reverts and inverses all these transformations to give us the inputs that we want to look at. And we'll discuss what kind of tools, heuristics, and optimizations we can do to make it actually feasible and scale it up to larger systems so that we can actually work with real programs and not just little 20-line toy programs that some of the papers are talking about. So after the motivation, as a next step, I will quickly introduce symbolic execution as a technique, how it works, what kind of tool exists, and maybe hint a little bit at the limitations of these tools. So what actually is symbolic execution? So on one hand, it's an abstract interpretation of code. Instead of using concrete values, when we execute individual instructions, we use symbolic values and carry these symbolic values along the execution of the program. So we kind of virtualize it, and instead of concrete values, we use symbolic formulas that get longer and longer the more instructions that we execute, and with all the additional side conditions and so on that we carry along. Also, it's agnostic to concrete values, as every value that we have, every concrete value, turns into a formula. And if we have additional constraints, like an and with some value, some static value, or some selection or anything like that, then the concretization helps to reduce the complexity of the formulas that we have to carry along. And the goal is, if we finish the transformation and can produce a specific condition that holds to all the paths along the way, we can find the set of concrete inputs that will actually fulfill the condition that we have in the end. And we can then use this one to trigger some interesting condition. So let's drink the Kool-Aid and look what we can do with it. So for our vulnerability, for our example, we define a set of abstract conditions at specific code locations. And symbolic execution is then used to trigger an input, to generate an input that we can use to actually trigger that vulnerability at this other location. And there are two kind of ways that symbolic execution is used for. And one of them is testing, so for finding bugs in applications. And the conditions that we encode are a set of preconditions and post-conditions that we want to hold at specific locations. So maybe a specific condition would be that the return instruction pointer on the stack is never overwritten with some other values. Or we use the assertions that are already in the code, and we use symbolic execution to ensure that there's no input that can trigger these assertions under these specific set of conditions. Or another option is to use symbolic execution for exploit generation. So we have a set of conditions. If these conditions would hold, then we would be able to exploit the program in one way or another. And we then use symbolic execution to generate the input that triggers this safety violation on the higher level. So our goal is to kind of revert or let the machine do most of the work while we only define a set of conditions we're interested in, and then let the machine do all the work and let us just look at the final result. What kind of tools are out there? How does the gang look like that we have? So there are three major symbolic execution tools that all cater to different needs. One of them is Fuzzball, the one that we developed at UC Berkeley. And we are selling it as a tool for proof of concept exploit generation. A proof of concept exploit is not something that is exploit that you can shoot out and execute your code right away, but it just triggers a condition. Maybe it overwrites the EIP and redirects it to somewhere else, and you can then use this one to bootstrap it further on. All these tools are open source, of course, and you can download them and play around and do your own stuff. S2E, another awesome tool developed at EPFL in Switzerland, which offers you selective symbolic execution on a large-scale system. And you can trigger these symbolic values along the execution of larger applications and systems. And CLE, another symbolic execution tool that's been sold to or developed to find bugs in applications and in source code and so on. All of those, as I said, are open source, and many of them have helpful information how you can bootstrap and get along. So now that you know that the concept of symbolic execution a little bit, I want to give you a concrete example so that you can actually see what the power is. And what better example than one of the Vortex war games? These are hacker games where you have to try to exploit specific conditions in programs. And they're really good to develop your skills and get used to coding and vulnerabilities and so on. And I thought, well, I don't like to think that much. So let's see if we can use symbolic execution to actually help us solve one of these war games. And this one is one of the early ones. I guess it's number 1 or number 2 or something like that, out of 30-ish. And it's a program that reads an input, transfers it, does some stuff, and then triggers a shell and drops you into a shell. And if you look at the code a little bit, we see that somehow we have to override the pointer with OXCA, and then we'll trigger our win. So how can we trigger that? It's down at the default case in the big switch, where the input is looped through and executed. And let's see, we actually have a write vulnerability where you can actually write some values into memory that are protected by a guard so that we cannot write after the end of the buffer. But luckily, we can write before the buffer. And we see that pointer is initialized with a static value. So we know the address relative to that other buffer. We can, using a special character, we can decrement the pointer and move it back and forth along the executed code or along memory. And in the end, it looks like this. Pointer points to buffer. In our switch case, we have 3 different versions: a ternary selection between a debug output, decrementing the pointer, and either triggering our win or writing a value to memory. This sounds still very abstract, and the problem size is 3 to the power of n that we have to walk through. And we'll just look at a quick demo, and I hope that I can switch over. Yeah, looks good. So we do have our code here. Instead of dropping us into a shell, I changed it into a clean exit with an exit number 23. Just makes it a little bit easier. And I help symbolic execution a bit by allocating the buffer at a specific offset instead of at a random address. And in the end, we'll just walk through the buffer and let symbolic execution handle it. I removed the debug output. So if symbolic execution engine would trigger the debug, I don't want to clutter the screen all the time. So let's compile it, and let's see what kind of stuff it generated. A large set of conditions. We started in our symbolic execution engine. We assume a Linux system call model. We virtualize the different components. We set 6 symbolic input bytes at our input buffer that we want our symbolic execution engine to generate. And we give it a start address where we start the symbolic execution and an end address where we end symbolic execution. And let's just run it. So the system initializes. We have a set of system calls. And now it's trying different inputs. It tries to follow all the different states that are possible and tries to generate an input that will trigger our win at one point in time. And you see that all these 001s that you see scrolling by are generic inputs, and it works through the backslash that triggers the decrement, write values, and specific debug prints. It removes the debug prints pretty soon. And now we see that it's already finished in roughly 22 seconds on this poor little netbook that I have here. And it's running on the netbook, not on the cluster. And we see that it generated a set of backslashes to decrement the pointer. It writes an OXCA which is 202 in decimal. And then you can write any value to actually trigger the win condition. And we've just used symbolic execution to solve a vortex war game in 3 minutes, which is kind of nice. When I solved it the first time, it took me like 3 hours or so. So that makes it a bit easier. But let's continue. So we now know what symbolic execution is capable of. But how far can we stretch symbolic execution, and what are the limitations that we'll run into? It looks kind of a nice tool, right? So if we could just use it to write our ROP exploits or ROP slides for us, that would be perfect, right? But unfortunately, that's not going to work. So we're going to look at the different limitations regarding the input size, the amount of symbolic bytes that we have, and the amount of code that we can cover symbolically, because we always have to execute it symbolically using some execution engine that has a high amount of overhead. So how far, or does symbolic execution scale? And if so, how far does it scale? We start using a simple example, and we use run length encoding, which is one of the simplest compression formats that you could think of. It was invented in the 70s for to encode fax images and stuff like that. But it's still a valid encoding in all the PDF formats, and any PDF reader has to actually implement it in this spec. We assume that the output is given, and we have a decoder function. But we want to have a specific input that then decodes to our given output if we only have the function that decodes. So we use symbolic execution to compute the pre-image to a given output. And we evaluate the performance of CLI and Fuzzball, two of the bigger symbolic executions engines that we could just run on top of it. And we implemented RLE the same way as it is implemented in PDFs. So let's look at how far symbolic execution actually scales. On the x-axis, we see different configurations for this simple benchmark with input and output lengths. So 3 input bytes, 3 output bytes, up to 5 input bytes and 3 output bytes. And on the y-axis, you see the runtime in seconds. And remember, it's a logarithmic runtime. And we set a 10-hour limit. So as soon as we scale up the input sizes, we see that the output, the time we need to run the experiment goes up. And if we are using only 7 input bytes that produce 9 output bytes, we already run a couple of hours. So vanilla symbolic execution does not scale if we use it that way. We'll run into the state explosion, and we cannot invert these processes. So we have to get around that somehow. We just run into the state explosion that we follow at each decision point in a control flow graph. We follow all the passes that follow this decision point. So if we have a simple control flow graph here, and we start executing from the top, first of all, the symbolic execution engine follows one single condition and updates all the passes and constraints along the way. Then we have to follow both the second and the sixth point. So we already have 2 paths. We continue. Just on the right-hand side, we have more and more passes that are joined together. We continue, and we see that the longer we execute it symbolically, we have to carry on all these constraints, and the formulas get longer and longer and longer. And that's how we run into the state explosion. And the problem is that we cannot decide which ones are more interesting to follow and which one are not. So we're basically drowning into the sea of tears, just like Alice did. And we want to know what the reasons are and how we can get around those. So one of the reasons for the state explosion is there's too much input or output data that we're interested in. And there's not much we can do about that. That's why we wanted to scale in the first place. The other reason is that there's too much included state. So we have to limit the amount of symbolic state that we carry carry around. And there's too much executed code in one go. So it gets too complex for the symbolic execution engine. And we have to use a divide and conquer strategy to split it up into multiple steps. And we're going to see how we're going to do that later on. So let's scale it up. Instead of just 7 symbolic input bytes, we want to have more. We want to solve the problem in the first step using some set of heuristics. So if we can encode somehow specific conditions that help us in the symbolic execution process, how far can we go then? How far can we scale it up? If code behaves according to a set of properties that we define in the next step. So what are interesting input sizes for us? How far can we scale it up in this limited space of computation that we have available? 10 symbolic input bytes. Well, this is kind of an address, an offset, or a pointer or two, but not much more. We can already do that with the existing symbolic execution engines. Other options, if you have 20 to 80 symbolic bytes, we can actually invert some shellcode, a small ROP chain or something like that, but unfortunately not much more. And that's already the limit if you have a lot of computation available that you can do with current engines. Well, and if you want to have more than 200 symbolic input bytes, we can encode long ROP chains at our vulnerability condition, or even complete data structures that are present at our vulnerability condition and flow through the application until we hit that condition. So first of all, heuristics to the rescue. Let's assume some properties on the code, or let's assume that the code follows some well-defined properties for specific transformations. And we looked at a whole bunch of code blocks that transfer input data in one way or another. And most of the transformations are surjective. So there exists a transformation. So for a compress function, there exists a decompress function. For an encode function, there's a decode function. For image decoding, there's an image encoding, and so on. So we assume that this holds. We also assume sequentiality. So as soon as our code transformation writes a specific input byte, we assume that this output byte will never be revoked. And we also assume that transformations are streaming. So the amount of symbolic state inside the execution engine is bound and does not rely on the complete input data that's available. And if these transformations hold, then we can do some tricks, and we can use some specific heuristics to cut some corners. And some of the heuristics that we use is to prune early and prune often, as soon as the target becomes unreachable, and just drop these states that will never reach our goal. Another one is to be greedy. So if we see that one specific state or one specific path that we follow in the symbolic execution engine produces a lot of symbolic output bytes, or a lot of output bytes that we desire, we'll actually prioritize this path in our search and try to follow that one deeper into the rabbit hole to get as much output data as we can. And we do some specific optimizations for array accesses by combining formulas or splitting formulas depending on a set of conditions. But you can read about that in a paper if you're interested. So if we encode these heuristics, how far does it scale? So we use the same transformation as before. This time we use 3 configurations: CLE, fuzzball, and fuzzball with our newly encoded heuristics. And we see, well, it's not too bad. We are doing much better than the unoptimized version. So we still see some kind of explosion, but it's not as bad as before. So heuristics help, well, a little. But the state explosion still remains. And we have to cope with that further. So let's see if we can use a divide and conquer approach to break it up into smaller steps. Heuristics got us so far, or that far. Now let's take a data structure or data-centric approach and split the process of computation of computing the pre-image into several smaller steps, and we tackle each step on its own. So we have the same program, abstract program, with a vulnerability condition as we had in our motivation. And we know that the input flows through that application to reach the vulnerability point in the end. But this time, we know that just using one symbolic execution process is not going to work. And it's going to run into the state explosion, and we're not going to be able to produce anything that's interesting. So we actually have to take a different approach. And by following a data-centric approach, we know that input is processed in each program in several steps. So first, the input is copied into one input buffer. Then there's some transformation onto the data before it is copied into the next buffer. After that, there's another transformation, and it's copied into the next buffer. And at one point in time, we'll reach the vulnerability condition. So now, instead of using one big chunk of symbolic execution to compute a pre-image in one go, we use several chunks of symbolic execution and concretize the values at each decision point that we figure out. So we use several steps of symbolic execution to compute the pre-image in the end and trigger and solve this problem. So again, does symbolic execution scale if we use this approach? And this time, we use two transformations, which are both valid for PDF files. First, we use hex decoding. So we have a long hex encoded string that is first hex decoded by the PDF library, and then RLE decoded to display an image. Imagine we have a digitalized fax message somewhere embedded in a PDF, and both hex encoding and RLE decoding are valid PDF transformations according to the PDF specs. And we start with the second location. So with the second transformation, we first do the RLE decoding and then the hex decoding. And we'll look at the different configurations of these three applications again. So let's look at the code itself in a simplified way. We see that input is copied into the first buffer, buffer 0, and then the ASCII hex decode, the decoding writes into the buffer 1, and then the buffer 1 is decoded using RLE decoding into buffer 2, where we might trigger a vulnerability at one point in time. And we constrain symbolic execution to one transformation at a time, and the symbolic input bytes only have to flow through one transformation. So we have the buffer 0, we go through hex decode. We have buffer 1, we go through RLE decode, and then we end up with our win condition. And we use two steps of symbolic execution. So let's try a quick other demo. I guess I have a couple more minutes, hopefully, which should be enough for that. Oh, that's the wrong one. Yep, here we go. So we have our decoding, and let's just copy that part, not all of it. No. I'm doing that on purpose, you know. Stop. Yes, here we go. And we're going to first decode the RLE buffer, and we want to produce a string. 33C is awesome, and we let the symbolic execution find out. So the symbolic execution engine knows about the RLE decoding, and it's trying different kind of states. And with RLE, you see if there's no repeat characters, then the first byte encodes the length of the string. Then the string follows, and then there's a specific end byte. And in this the configuration that PDF uses, it's 128. which is OX80. And our symbolic execution engine successfully reverse engineered the RLE encoding process using the RLE decoding. And we can do the same thing for the hex decoding. But I'm not going to try to copy the other part again. Otherwise, I'm going to run out of time. So I'll actually upload all these examples so that you can try them out later on. So let's see how far we can actually go with this encoding. And this time we have hex encoding and RLE decoding, so 2 steps. And we compare it again against fuzzball without the configuration as a monolithic approach, and CLI as well. So it gets a bit more complicated this time. So we have input bytes, intermediate bytes, and output bytes. So there's a first transformation from output bytes to intermediate bytes, and then a second transformation from intermediate bytes to input bytes. And we have a set of different conditions that we try out. On the y-axis, again, we have the logarithmic scale. And again, a 10-hour time limit on our cluster for single core computation. So what we see is, well, monolithic symbolic execution engine, as used by CLI or fuzzball, runs into the 10-hour time limit every single time for these configurations. If we use our heuristics, no, we're doing a little bit better. We scale up to 20-ish bytes, input bytes that we can cope. If we use our two-step approach, where we split according to the different transformations, we can scale up to 250 hex bytes that we encode and 120 intermediate bytes, which is good enough for a reasonably sized data structure that we can carry along. And we see that this works fairly well. So we have one problem solved. Divide and conquer mitigates the scaling issues. But we now have 2 problems. Finding the transformation boundaries, how do we do that? And finding the buffer locations. How do we get that? How do we know where they are? Especially if we only have binary code or some executable. So let's see what we can do. And let's use some binary analysis technique for that. So where should we split these symbolic execution units? And we use a graph-based binary analysis approach to find minimal points along the execution graph of the application, where we have little interference between individual transformations that transform the data that is available. So on one hand, we have a control flow graph, but we combine this control flow graph with information or data flow graph on the other hand. An information flow graph encodes how information flows from one buffer to another buffer. And these 2 data structures already exist, but we add additional producer and consumer edges along these 2 graphs so that we can use the combined graph to decide what the best points are to split individual transformations. So we know that buffer A will, basic block number 2 will read from buffer A, and symbolic basic block number 4 will write to buffer C. So we know that there's an information flow from buffer A to buffer B, and we can use these informations to know or infer that there's a transformation from buffer A to buffer C, and we can follow that one. So how can we recover this graph? And we just use a simple trace-based binary analysis on top of that. We collect a detailed instruction level trace of a concrete execution that executes functionality that is close to the vulnerability, but does not trigger the vulnerability itself. Otherwise, we would already have solved the problem, right? So we execute a simple version of like just a PDF viewer and encode the execution trace and use that execution trace to see how the input data flows through the application. And using that execution trace, we can follow all the individual buffer accesses and concretize those. So we start with a concrete input. We collect the instruction level trace. We process the trace offline to discover all these individual buffers and set the combinations between the buffers. So problem is, if we are working with machine code, we have a huge amount of memory accesses. And we need to organize them somehow. And we do this using a hierarchical concept where we have different levels and categories of buffers. So related memory accesses target the same buffer. There's maybe a temporal or a spatial location. Temporal according to the access log of memory access that we have, or spatial according to the code that we have. And in our analysis, we can actually use both these kind of accesses to group related memory accesses. And we assume this buffer hierarchy as a level of buffers. So there's the complete memory image, there's the stack, there's an individual stack frame, there's a struct in a stack, and there's a specific buffer in that struct on the stack. And we find natural boundaries between transformations to split up our symbolic execution. As a last example, we're going to walk through a CV, a real vulnerability, where we have a font parsing bug in a popular PDF viewer. That's a fairly common PDF library. And if we look at the memory accesses, it's insanely complex. It would be very hard from a vulnerability point of view if you only have the binary to actually follow these individual steps until you hit the condition. So there's I/O processing, there's the FLATE decode that's happening, the font reading part, and the font parsing part. And the bug actually happens in the font parsing. But how do you generate such an input? How can you actually produce that? And we ran our magic Python script on the trace we collected and split the symbolic execution along these paths and came up with a set of several symbolic execution processing steps to produce that image. First, it's the mem copy that copies from buffer A to buffer B, from the input buffer to the parsing buffer. Then we are able to decode the FLATE encoding. We read the font into a buffer. And in the end, in the font parsing part, there's the vulnerability. And we're actually automatically able to produce input that triggers that vulnerability, that follows along these different steps, according to the splits that we have in our graph. So selecting the individual parts from the graph that we have is still needs some manual work, but it works fairly well. And you can actually try it out for yourself. So what did I show you? First of all, symbolic execution is no panacea for every problem. That you cannot just throw stuff at it and let it solve it. You have to be aware of all the structural differences. And due to all this additional overhead, it doesn't scale that far. But if you look into the individual transformation or the kind of code you're trying to reverse, and you're aware of some graph-based analysis on top of it, then you can actually scale it up to real data structures and do real things. You can trigger, as shown in this example, you can trigger vulnerability conditions that you define that are deep inside the program and hidden. And you can actually construct some proof of concept input that will trigger this vulnerability in the end. And you can explore how deep the rabbit hole goes for yourself. You can download all the software from the website. I'm around on a CCC. Just talk to me. I'm happy to discuss anything in more detail. Thank you for your attention, and I'm happy to take questions. Thanks.
We have around 10 minutes for question and answer, if there is any. Yep. Microphone 1.
Hi. Excellent talk, by the way. So my question is in relation to the ease at which one can recover these opaque predicates that you seemingly recover automatically. So another developer of a related project, BAP, came by Noisebridge, a San Francisco hackerspace, and he showed a demonstration of BAP, which is of course very similar to BitBlaze, recovering the Aurora vulnerability, which is I think like Git font icon. And it seemed that a considerable amount of the work that he did in BAP and Microsoft Internet Explorer was actually like writing SMT-lib code, which like you can feed into Z3. And it seemed that a considerable amount of the work that was performed actually had to do with a lot of knowledge that he had about the vulnerability well after the vulnerability had been published. So it seemed that the majority of the work was done by like Z3 or some other equivalent SMT solver. And then BAP kind of had this ancillary role that didn't seem to be recovering these neat things like tracing a return code as it gets passed through the program. So I guess what is your opinion, if I'm going to ask a concrete question, what is your opinion on the limits of like concolic execution or Bitblaze on truly generating exploits automatically without a great deal of knowledge about the nature of a vulnerability or the program that it runs in?
First of all, I'll be very happy to talk with you about this offline for hours. Okay. But let me give a very short and brief answers. So in this talk, I gave the motivation that we already know the vulnerability. So we know at which instruction the vulnerability is caused, and we know the code. We can look at the instructions prior to that access, and we can actually encode these instructions. So we know what kind of conditions happen at this vulnerability. We just want to produce a pre-image that flows through the application that executes that vulnerability. And you're perfectly right. Symbolic execution has a hard time encoding these properties. And it needs a huge amount of manual effort and work if you use it to find the vulnerabilities. So I'm not 100% sure if symbolic execution is a perfect tool to find the vulnerabilities. You can use it to generate pre-images. That's what it's here for. But you will need additional logic and manpower to encode it to find the vulnerability conditions itself.
Just a quick follow-up. I'm sorry.
Let me give a quick, blatant commercial interruption. So there's bounded model checking. And you can use bounded model checking to infer a nice set of vulnerability conditions. And we're moving more and more to use bounded model checking to actually come up with the actual vulnerability conditions that we can then feed into the symbolic execution engine on the other hand.
Do you want to ask a follow-up?
Are there other questions?
Yes, here. Please go to microphone 2.
I was just trying to refer to the guy who was talking about Z3. Z3 is very interesting and it's very intelligent program in a certain sense, but to be honest, I'm not really sure it's the best topic to talk about in a conference like this because it's closed source, developed by Microsoft, and they really.
You're ranting about Z3?
Sorry?
What are you ranting about? Z3?
Z3, yeah.
Yeah.
So
we support Z3 and STP, so you can use any solver you want.
Yeah, I suggest you use STP.
Yep. The drawback is STP is half as fast, right? So.
Yeah.
Could you handle arbitrary state explosion added by obfuscated code or things like that? Do you have some way to detect that some code has no influence in the result? Or?
You're talking about deobfuscation of. Let me rephrase your question if I got it correctly. So you assume that you have some obfuscated executable, and you want the symbolic execution engine to get rid of all the superfluous computation.
Not to get rid, because sometimes you just can't. But is there some way to crash the state space to eliminate some part of the obfuscated code path?
Well, a lot of the heavy lifting is actually done by the constraint solver, right? So if under specific conditions no computation happens, the constraint solver should simplify the formulas and throw away those. So that happens intrinsically in the solver itself. So we don't have any additional checks that help in that regard. And we focus mostly on binary-only code, but not heavily obfuscated or packed code. You can try out and tell me about it afterwards.
Your last one.
Just a quick question. How much memory does it take to keep track of all the paths you went through?
For Poplar, I guess we used something like 12 or 16 gigabytes, so not too big. Well, RAM is cheap, right?
Okay, I think we are running out of time otherwise.
Awesome.
So,
If you have other questions, just catch me somewhere around the
Yep.
CCC. Thanks.
thank you.